Dear all, I am Dr. V. Malati, Associate Professor, EC Department, SR University, Warangal. Today's lecture is on ECG signal acquisition and analysis. In this, we are going to simulate raw signal, which is a graph of time in second versus voltage in amplitude. Then, filtered ECG with QRS complex detection. It is also a graph of voltage in amplitude versus time in second. Finally, heart rate is determined and it is equal to be 63.32 beats per second. I have written code in Python. Now I am going to simulate using Google Colab platform. Now I am sharing the screen. Okay, we got the output. Now I am going to explain the code line by line. So first one, import numpy as np. So np is the numpy Python library. This library is imported from the numpy. And then import matplotlib.pyplot as plt. So wherever we see plt, this belongs to the output graph. We can draw a box plot or bar chart or histogram in image processing or ordinary graph, one parameter versus another parameter. So we can download, import pyplot from the matplotlib library, and then from scip.signal. So this signal functions are taken from scip module, and then import butter filter find peaks. So butter filter find peaks, these three are the functions of signals, and therefore the required functions are to be imported. And then sampling parameters. So fs is equal to 500. Now what is fs? It is sampling frequency. So the number of samples per second, it is equal to 500. And now t equal to np dot linspace 0, 10, fs into 10, which is 10 seconds duration. And x-axis is time axis, and the time starts from 0, ends at 10, and this 10 is uniformly divided. And how it is divided? 1 by fs, that is fs is equal to 500. So 1 by 500 is equal to 0.002 seconds. So starting from 0 and then 0.002 and then 0.004. In this manner, it is segregated and then simulated ECG signal. This ECG signal contains the components of P wave, T wave and then QRS complex. So here ECG is equal to 0.6 NP. So it is in NumPy Python dot sine 2 pi 1.7 t plus 0.15 into sine 2 pi 40 t plus 0.05 plus random number length t. And this is the first term is heartbeat rhythm. So our heartbeat rhythm is having a frequency of very low, that is 1.7 only, 1.7 hertz. And then muscle noise. So due to the contraction or expansion of our muscle, there will be some small amount of noise which is having a frequency of 40, and then this 0.05, it is amplitude. The same way 0.15, it is the amplitude of noise. 0.6 is the heartbeat rhythm amplitude, and then we are sampling the ECG signal. In the same way, this noise also should be sampled, and the length of the noise sample should be equal to the length of the original ECG signal. So uniformity should be maintained. So here this part represents one component of the ECG signal modeled using a sine wave in ECG simulation. This term usually represents low frequency component often associated with the basic cardiac rhythm or baseline waveform. When added with other sine term for P wave or T wave or QRS complex, it forms a more realistic ECG signal. So this shows that normally ECG is not the one and only input. See, the noise will be added, and then general sine waveform we have to represent as A sine 2 pi ft, that is A sine omega t, omega equal to 2 pi ft, and then A means amplitude. So next one is 0.6 is amplitude. It controls the height of the waveform, that is, it shows the signal strength. Here, it simulates the magnitude of one ECG component, and then it is used to simulate periodic biological signals. Frequency is 1.7 hertz. It means 1.7 cycles per second. So heart rate equivalent is 1.7 into 60, which is equal to the minute. That is why 60 we are taking. Normally second in the formula, but we have to convert it into minute. So 1.7 into 60, it is equal to 102 beats per minute. And then this mimics a heart beating around 100 beats per minute. So 102 is taken as 100 beats per second. And then 0.15. So it is the amplitude. This is another sine waveform component because we are writing the term sine. That is why sine wave component. So it is added to our ECG signal, but it represents a high frequency, low amplitude. See, it is 1.7 variation. But noise is usually high frequency, we know. That is why when compared to ECG, the noise signal is taken as 40 hertz. But amplitude is low amplitude. Still it is lesser than the amplitude of the ECG. So 0.15 and very small compared to 0.6. It means that this component has a very small effect on the overall ECG. It's often used to model fine details or noise-like variations. And then 2 pi. So it is 2 pi. Why we are adding this? It is conversion to angular frequency. Then 40 hertz. So 40 cycles per second is much higher than the heart rhythm frequency. So this lies in the range of QRS complex sharp variation. Muscle noise, actually it is EMG interference because electromyography, and then high frequency ECG components. So it means generate a sine wave with amplitude 0.15 and frequency 40 Hz. So in ECG simulation terms, the 1.7 Hertz term models a slow cardiac rhythm. The 40 Hertz term models rapid fluctuations such as sharp QRS spikes, electrical noise, muscle activity artifacts. Together, when added, we will get ECG is equal to slow heart rhythm plus fast small oscillations. This makes the simulated ECG look more realistic by combining low frequency main heartbeat and high frequency fine details or noise. So 0.05 NP dot random dot RANDN LENT, that means random noise. This term adds random noise to our ECG signal to make it more realistic. Now, breaking down it, how to explain? It generates random numbers from a standard normal Gaussian distribution. So, for all cases, noise means the reference noise is white Gaussian noise. So here the mean value is 0. So reference. So mean should be 0 and standard deviation is equal to 1. So values can be positive or negative. And then LENT, it ensures the number of random values equals the number of time samples. So number of samples per second, whatever we use for ECG signal, the same should be maintained for the noise also. So each time point gets one noise value, and 0.05 we know it scales the noise amplitude. It makes the noise small, so it does not dominate the ECG signal, because already the amplitude means it shows the signal strength. So the noise strength should not overcome the original signal strength. Standard deviation of noise becomes 0.05. So this means generate Gaussian noise with 0 mean and small amplitude 0.05 sample, and it added to every ECG sample. In signal terms, noise is equal to 0.05 dot n 0, 1. So 0 means 0 mean. Then in ECG simulation, this represents finally we get electrical interference, sensor noise, motion artifacts of muscle activity noise. Without this term, our ECG signal would look too smooth and artificial. So with a shutdown, our ECG signal becomes ECG is equal to clean ECG components plus realistic, not random noise. And then, so this operation has to be done for the entire signal, so that we are going to use a loop. For I in range 1, 10. So ECG int I into fs dot int fs plus 20 plus is equal to 2. So this code artificially adds sharp spikes to the ECG signal to simulate the QRS complex, that is R to R peaks. So we here for I in the range 1, 10. So the loop runs for I is equal to 1 up to 9. So next to 1, this means events are added at 1 second, 2 second, 3 second up to 9 second. Then I into fs. So we know that fs is sampling frequency, and that too we have taken 500 hertz. So I into fs, it converts time seconds into sample index. So example, if fs is equal to 500 and I is equal to 2, so I equal to 1 means 500, so I is equal to 2. This code artificially adds sharp spikes to the ECG signal to simulate the QRS complex R to R peaks. So here sample corresponding to 2 seconds when I equal to 2. So what will happen? It converts the index. So I means index to an integer. So it can be used to array indexing. Now ECG INT I into fs. So what is the meaning? Here 20 means, so select 20 samples starting from that time point. So with the fs is equal to 500, we get 20 samples is equal to 20 by 500. It is equal to 0.05 second. It is otherwise is equal to 40 millisecond. So 0.02 means already in the time waveform we told 0 to 10 means first number 0, second number 0.002, third number 0.004. So in this way we are dividing the 0 to 10 time axis. This short duration, why we are doing this? So the narrow width of the QRS complex. So here plus is equal to 2. So here what is the meaning? It adds the value of 2 to those samples. This creates a sudden high amplitude peak in the ECG. So it is our wish only to make it zoom. It is like equivalent to zoom. So the meaning is at every second from 1 to 9 second, add a short, strong spike of amplitude to the ECG signal. In ECG terms, these spikes represent R peaks, that is QRS complex. Already R is peak only, but still we are making it to go up for the recognition. They make the ECG waveform look realistic by introducing sudden sharp peak. So when we take a print in the ECG paper, that R peak should be visible, because R to R, in between two R's, there will be it is grid paper only. Small squares, large squares will be there. So heart rate will be found out by counting the number of large squares in between 2 hours. So that is the formula is 300 divided by number of large squares between 2 hours. That is why that R peak is still exaggerated to get the sudden sharp peaks. A regular heartbeats at 1 second intervals. So heart rate normally it is equal to 60 beats per second. Without this code, our ECG would be mostly smooth sine waves and noise. With this code, it gains characteristics sharp heartbeat peaks of a real ECG signal. And then define band pass. So, a bandpass filter is taken into account here because we know that bandpass filter means it will have lower cutoff frequency and higher cutoff frequency. So, below the frequency components below the lower cutoff frequency will not be allowed to pass through the filter. In the same way, the frequency component above the higher cutoff frequencies will not be allowed to pass into the filter. So the below lower cutoff frequency, those signals will be called as stop band. In the same way, the signals above the higher cutoff frequency will be called as stop band. But the components lying in between lower cutoff to higher cutoff, that is FC1 to FC2, those signals are called as pass band because they are allowed to pass through. So now what this line says, it is signal comma, low cut comma, high cut comma, FS. So it is sampling frequency as we have already defined as 500 and the order is equal to 4. The order of the filter is taken as 4. It is extremely high. It is not 1 means no problem, nothing. 2, 3 already it is higher order only, but 4. So the steep filtering will happen. So that is why it is higher order filter. And now the signal is the input data to be filtered. That is our signal array, ECG signal array. And then low cut is equal to low cut of frequency in hertz. Frequencies below the values are removed. And high cut means upper cut of frequency in hertz and frequencies above this value are removed. And then Fs is equal to sampling frequency needed to correctly design the filter, and the order is 4. It is default for all EMI. We are taking the 4 as the order of the filter, and it controls how sharp the filter is. So higher means the filter becomes sharp, so it will do the sharp filtering. So higher order sharp filtering, but more computation complexity okay, but filtering will be good. So 4 is the common practical choice for ECG processing. So in simple words, this function means create a function that takes a signal and keeps only the frequency components between low cut and high cut using 4th order band pass filter. And then here typical value low cut is equal to 0.5. So it removes the baseline band. Now high cut is equal to 40 hertz. It removes the muzzle noise and high frequency interference. So high frequency means noise, so higher frequency. So above 40, those components will be assumed to be noise components, so that they have to be removed. So when you later call filtered ECG is equal to band pass ECG, 0.5, 40, Fs. It means filter the ECG so that only frequencies between 0.5 and 40 Hz remain, which is the useful ECG band. And then Nyc equal to 0.5 into Fs. So it is the Nyquist frequency, it is the maximum frequency that can be correctly represented in a digitally sampled signal. So, if our signal contains frequencies higher than Fs by 2, they will cause aliasing, that is a distortion. It is one type of undesirable artifact. it compute the maximum usable frequency of the sample signal. So low equal to low cut by Nyquist. So high equal to high cut by Nyquist. This converts, why we are dividing the frequency by Nyquist means converts the real world frequencies into normalized values in between 0 and 1. So finally the value will lie in between 0 to 1, so that whatever it will be the frequency we have to normalize and they will come under 0 and 1. This the filter design functions like butter require butter of the filters like that need that only. And then B comma A. So filter functions. So filter means filter functions coefficients we have to generate for filtering. So B comma A equal to butter open bracket order comma low comma high and B type equal to band. So order means it is 4. Low means we know already determined. High means we know already determined. B type, that is Butterworth filter type, is here band pass filter. And then return filter B comma A comma signal. So B means numerator of the coefficient. A means denominator of the coefficient. And filter means it will filter the signal very smoothly, so there will not be any phase distortion. So no distortion, that is the filter. So next one. So in this way, it creates a Butterworth bandpass filter of given order that only keeps the frequencies between high cut and low cut. So high cut and low cut and store its mathematical parameters in B and A. So return filter B comma A comma signal. This line applies the designed filter to the signal and returns the filtered output. That is why the filtered output is returned from this line. And the filter means what is the special properties of this function? It is forward and backward filtering. So to and fro. This filter is applied 2 times. Once forward in time and another one backward in time. This removes phase distortion. No time shift in peaks like R peaks in ECG. So B comma A, we know that filter coefficients form. Filter the signal using the Butterworth bandpass filter in a zero phase manner and return the cleaned signal. That is why we are using filter. So R peaks remain at the correct position. Normally, it is used in the biomedical signal analysis. It will give the noise reduced ECG signal without distorting the timing of heartbeats. So next one, filtered ECG is equal to and bandpass ECG 0.5, 40, Fs. This line calls the bandpass function to clean the ECG signal. So what is the meaning? So ECG, we know it is raw ECG that contains heartbeat information, baseline drift, high frequency noise. And what is 0.5? We know low cutoff frequency. It is baseline matter, respiration, artifacts. And then 40, we know higher cutoff frequency. And then a noise like muscle contraction, power line interference, and then instrumentation noise. Fs, we know it is a sampling frequency needed to design the digital filter correctly. So this means filter the ECG signal so that only frequencies between 0.5 Hz and 40 Hz are kept. So next one, peaks underscore is equal to find peaks filtered ECG. Height is equal to height is equal to 0.8, distance is equal to fs by 2. This line detects the R peaks, that is highest point in the filtered ECG signal. Let's break it down. Filtered ECG means the ECG signal we want to analyze after filtering. Height is equal to 0.8 means only consider peaks that have a value greater than or equal to 0.8. So less than 0.8 means R peak will not be considered as peak and it will be ignored. This ignores the small bumps and noise. So it ensures only prominent peaks are detected. So peak only detected. So others irregular, that means assumed peak will not be taken into account. And then distance is equal to fs by 2. It is maximum distance between peaks, that is fs by 2 samples. If fs is equal to 500, then fs by 2 is equal to 250 samples, that is equal to 0.5 seconds. It prevents detecting multiple peaks in a single heartbeat. It ensures that two detected peaks are at least 0.5 seconds apart. So that is why to make the separation we are doing like this, which is realistic for human heartbeats. That is less than or equal to less than 120 beats per second. And then finally we are doing plot, how to plot. So plot figure is equal to figure size 12 length 6 height. So plot dot subplot. So two rows and one column. So the first position is plotted time versus ECG magnitude. So the title given to it is raw ECG signal. And then x-axis we know that time in second, y-axis voltage in amplitude. And then subplot in the second position. This is also plotted time versus filtered ECG, and then plot peak divided by fs, and then filtered ECG peaks RO. So the title given is filtered ECG with QRS complex detection. So time axis we know S only, time in second, y axis it is amplitude, voltage, and then tight. So tight means the diagrams are arranged in a tightly fit order, so equal distance, looking neat. So plot dot show it will be seen, visible, and then finally graphs are shown, but it calculates heart rate is equal to 63.83 beats per minute. So with this we conclude the simulation. We understand how the ECG waveform is simulated, and from that heart rate, how the human heart rate is calculated. Thank you.